Okay, so a couple of examples for this one here. Blue light shines on a metal surface, causes a photo emission of electrons. Didn't have to mention that. If a stopping potential, so a stopping voltage here, of 2.6 volts is required to completely prevent the electrons from reaching the collector, so the other plate on the other side, determine the maximum kinetic energy of these electrons. Okay, that's not too bad. So to do that, what I'm going to do is I'm just going to write down some stuff that we have here. So we have a V stop of 2.5 volts. Okay, we have the charge of an electron, because we're going to need that later on, of 1.6 times 10 to the negative 19 coulombs. And we're trying to find this EK max here, which is just going to be the charge of an electron times the V stop. Okay. Now, the thing is, most of the time when we talk about this EK max, if I'm communicating it, I want this to be electron volts. If we do the math here, we're going to get this in joules. Most of the time when we talk about EK or EK calculations, we're in joules. So 1.6 times 10 to the negative 19 times 2.6 ends up being 4.16 times 10 to the negative 19 joules. Now, if I want to convert that into electron volts, it's going to end up being 2.6 electron volts, because that's what the definition of electron volt is. It's the amount of energy an electron would get from rest across a parallel plate system, right? Which would be it's pretty much the exact opposite, rather than accelerating towards the other plate, it's decelerating and slowing down. But both those situations end up having the same energy change. But if I wanted to do the calculation here, I'm just dividing by 1.6 times 10 to the negative 19 joules per electron volt. And then I can get that number there. Okay? Yeah, it says express your answer in both joules and electron volts here. It ends up being the same number if you did that, because you multiply by 1.6 times 10 to the negative 19, then you divide it by 1.6 times 10 to the negative 19. Different units, one's coulombs, one's joules per EV, but they're the same number, so mathematically they end up just canceling each other out. The units don't, though, but the numbers do. An experiment shows that the work function of cesium is 2.10. Now, I don't know if that's true. The lab you do, you're going to do it for cesium as well, but you're not going to get that number. You're going to get a different number. And I think you'll have to do some research to find out what the actual number is. I think it's lower than this number. Determine the threshold frequency and the wavelength for the photons capable of producing a photo emission. So this is my work function, okay? So that's W. I can use H and F, or I can use HC over lambda. I'm not going to do that. I'm going to do the slightly different here. So I'm going to use this formula, first of all, to find out my threshold frequency. So my F naught here. So work divided by H. So 2.10 electron volts divided by, because this electron volts, the 4.14 number. So I got 2.1 divided by 4.14 e to the negative 15. So I get a frequency, a threshold frequency of 5.07 times 10 to the 14 hertz. And then I'm going to use the universal wave formula here, F lambda is equal to C, to find out what my wavelength is. So the speed of light divided by this number ends up being 5.91 times 10 to the negative 7 meters, which ends up being 591 nanometers. Okay, here we go. Blue light of 410 strikes a metal surface which has a work function of 2, so it's like cesium of 2.1 electron volts. What is the energy of in this case, the kinetic energy? Let's just mention that here. What is the kinetic energy of the emitted electron? So first of all, I want to determine, is this enough energy to get the electron out? Okay, so in a previous video, I mentioned that for a photo emission to occur, I have to have the energy of the photon has to be greater than the work function, or the threshold, the frequency of the photon has to be greater than the threshold frequency. Okay, so I'm going to determine what the energy of this blue light is first. So the photon is going to be h times c divided by lambda, hc over lambda here. Because this work function is in EVs, I'm going to use the 4.14 number times 10 to the negative 15 times by the speed of light. Oh, I should probably turn on my Google Meet soon. And divided by my wavelength. Okay, so 4.14. Oh, hopefully this is going to be enough. Otherwise, you can't do the question. It should be a 15, not a 5. Why is that? Why do you like that? There we go. Times 3 to the power of 8 divided by 410 times 10 to the negative 9. So change into meters. So I get a frequency. This is the photon energy of 3.03 electrons. That's the rounded number. I'm going to go back down later, not use the rounded number. But this photon energy is enough. There's enough energy to at least get some of the electrons out, the ones at the closest to the edge, because they only require 2.1 electron volts to get out. This has way more than enough. So I'm going to use the conservation energy formula that says the energy of the photon is equal to the energy required to get out plus the energy left over for the kinetic energy. So this is the electron stuff on this side. Okay, so that's the conservation of energy. So I'm just going to rearrange this to find out what EK is. This is EK max. Okay, so E photon minus the work function. So this is going to be 3.03 electron volts minus the 2.10 electron volts. Got the number in my calculator, so I'll just go minus 2.1. So this kinetic energy of this very particular maximum electron here is 0.929 electrons. There you go. Doesn't seem like that much, but if you want to, you can now convert that into joules and change that into speed. So maybe just quickly do that. So I change it into joules if I need to do this for a calculation later on, which I might have to. So I'm going to times by this number this time. And I'm going to get 1.49 times 10 to the negative 19 joules. There we go. Then I could use that to calculate speed and stuff. Cool. Let's do a few more here. So we got, let's do one more. So we determine the maximum. So this is the same thing I was talking about, the previous question. Determine the maximum speed now. Okay, so aluminium surface is being having some light on it, a UV light in this situation. Yeah. Obviously, this doesn't happen in visible light. Aluminium doesn't just eject electrons all the time. If it did, then everyone would be getting shocked all the time whenever they stand up from a desk or they go and touch a metal cup or something. So you need a higher energy photon to get it to emit electrons. Because when you emit electrons, you become a charged surface, or you could discharge a surface, one of the two. So let's determine the maximum speed. So to find the maximum speed, I'm going to have to determine the kinetic energy so I can find the speed. That should be a lowercase v. Oh, okay. There you go. So we've got the work function, so that's W, 4.08 electron volts. We have the wavelength of 125 nanometers, so that's definitely outside the visible spectrum. They tell it's UV already. I need to find this EK so I can find the speed. Okay, so let's first of all find the energy of the photon. Sounds like a good thing to do. So the energy of the photon is going to be hc over lambda. I'm going to use the 4.14 number here. I'm not going to write it out this time. And I'm going to change the nanometers into meters. So I'm going to get an energy here of 9.936 electron volts. Okay, so definitely enough energy to get this electron out. Okay, so using this other formula, E photon, the conservation of energy. This formula, this conservation energy formula I keep mentioning, is not on your formula sheet. It is something that you should try to figure or remember, or possibly just write on the top of your formula sheet. I'm okay with that. You'll see this on some tests here. They might use different, they might say, okay, this is a F naught here. This is HF for the photon. This is EK over here. They might substitute in the formulas for them, but we're not going to do that here because we have the numbers. So I'm going to rearrange this for EK, E photon minus W. So that's going to be 9.936 electron volts minus the 4.08 electron volts there. So minus 4.08, and you get 5.856 electron volts of kinetic energy. So this is the maximum kinetic energy here. I probably should mention that. It's always going to be the maximum. Okay. Scroll down here just a little bit. So now what we're going to do here, because for the kinetic energy formula, for this to work, this EK formula 1/2 mv squared, which eventually will turn into 2 times EK divided by mass square rooted, the EK has to be in joules. So I'm going to times this by 1.6 times 10 to the negative 19 joules per electron volt. So I'm going to quickly do that in my calculator here. And I'm going to get 9.3696 times 10 to the negative 19 joules. Seems like it doesn't seem like very much, but the mass of an electron is really small. So you have to remember that these are electrons here. So the mass in which I'm going to need is 9.11 times 10 to the negative 31. So I don't need that much energy to be going very fast. So I'm going to put that in here. 2 times this EK divided by my mass. Take the square root. So 2 times this number in my calculator, divided by the 9.11 to the negative 31. Make sure to take the square root, because if you don't, then the speed is way too fast, faster than the speed of light. But in this case, it doesn't end up being that way. So 1, 2, 3, 4, 5, 6. So 1.43 times 10 to the 6 meters per second. There you go. We'll just put down here, must be in joules. Joules is not capitalized either. J is capitalized when it's just J, but when you write out the person's name, it's not capitalized. There you go. Must be in joules for that to work. Okay, so the next video we're going to be talking about Compton effect and the strange property of massless particles having momentum. And I'll see you then. Bye.